Okay, well, I think this is all it's going to show up today. It's getting kind of sparse around here. Must be the end of the quarter. Okay, so just quick announcements just for the special folks who made it in class today. A reminder that project papers are due this Friday at 4 o'clock, right? They have to be turned in both to the Turnitin website on TED, but also I'd like a hard copy just in the box outside my office so that I can actually grade them over the weekend. And then the project presentations, those are going to be happening all of week 10, so next week. And so I'd like to have those to me by email no later than Monday, June 1st. That's for everyone, no matter what order you're going to be presenting in, which will be decided or pseudo-randomly, probably fully randomly, but we'll see how I get my random generator going. So presentations need to be June 1st. Now, if you have a product, like something that's like digital, that you can submit that way, I'd like to have those also by Monday. If you're building something that is actually a physical structure of some kind, you can bring that in during your presentation. But I would like to see a photograph of it turned in with the project presentation as well. I mean, obviously, if you have a presentation, you should probably like have some evidence of what your project is, so that sort of all hangs together. Okay, and keep in mind these are 5-minute presentations that we're going to be running through the lecture periods in week 10. It's 5 minutes plus a couple minutes for questions, which I think should cover all of that. Yes.
So everyone has to do a presentation, right? Not just the people who decide to do the presentation as a creative component.
So in the creative project, there's a balance between the presentation and the creative element, right? So if you put a lot of effort in the creative element, your presentation is really, here's what I made, here's how I made it, here's the process of it. It doesn't have to be a very formal presentation. If you're just doing a presentation, then it should be a formal presentation with slides and references and all this other stuff.
So if you're doing a product, then your presentation talks about...
Yeah, basically the process.
Okay.
How did you decide to make this poem or write this story? Like, what were your, inputs for that? Okay, and then reason I want these in by Friday because I'm going to read those over the course of week 10 and turn them back to you at the end of week 10. That'll give you a chance to do edits and revisions on those project papers by Tuesday of our finals week, which is the same time as the final exam. So this is totally optional, but if you look over the edits that I have for your papers and you want to turn them back in, you can get back up to half the points that you missed on the project. So obviously to get like a 95, this is probably not something that you want to spend a lot of time on. Devote your resources elsewhere. All right, but if you got a lower score, then that might be a good way of sort of bringing that score up, is to take the edits. Right? Now, again, the reason that this is based on midpoints is that this first copy really should still be a final paper. Right? If you turn in something that's very, very low quality, it's going to get a very low score either way, edited or not. So keep that in mind, that these papers, even on the Friday deadline, is still a final project paper.
Is there going to be like a separate Turnitin thing?
Yeah, I'll probably just make a separate revision Turnitin thing. It's just easy. One more comment I'll have, since most of you, when you turn in proposals, only like I think 1 or 2 of you actually use the Chicago style for the references. Make sure you use those for the final project paper. If you have any questions about that, there's a slide that we made for the workshop that's in the project folder on TED. We're using Chicago style for your references. Questions? Yes, ma'am.
Do you think that is it taking a picture of our project?
So there was a question about, remember that there was you can either do like a creative project, like poem, create something like that, or you can do a formal presentation.
Okay.
But even during our class, for those of who've done the creative projects, should also be presenting some description of what their project is. So, that doesn't have to be like a slideshow that's 10 slides long. It could just be standing up here and saying, here's my sculpture of the aliens from Venus, and here's how I decided to make the design choices I made.
Okay. So do we bring that product in on the day we present or like on Monday?
So if you have a physical product, you should bring it in for your presentation. If you have a digital project, so you made like a poem or a picture or even a movie, that should be that should be sent to me on Monday.
Okay.
Monday of 10th, not yesterday.
Okay.
Yeah. Yes, sir.
Some of the pictures in the presentation might have, do you want those from the primary source? Can I be more, like from like other places for like kind of like presenting Twinkle better?
There's usually not fantastic artwork in primary sources. So if you have a nice illustrative picture you're drawing from someone else, that's fine to use in the presentation. Just make sure you cite where it comes from. The bulk of the science you talk about should come from the primary sources, but the pretty pictures very rarely come from primary sources. Occasionally they do.
Also, do we have to cite, you know, cite the textbook?
You can, if you're drawing pictures from the textbook, that's fine. If it's, much of the textbook is already circulated material. So I would prefer if you could find the original source, but often that's not cited in the textbook. So I would say as a default, I would cite the textbook. Again, anytime you have an idea that's not your own, in general, you should be citing the source for that. The problem with textbooks is that they're actually not the textbook's ideas either. And they often don't actually put in the references except sort of deeply buried somewhere else. So do your best to find the original source. If you can't, I would say, this is from the textbook. That's fine. Any other questions about the projects? Okay. So there have been extra credit assignments, and this is Jacqueline. This is in response to your question on TED. If you happen to catch Woman in the Moon last week, there is now a place assignment where you can actually write your extra credit assignment. You have to have gone to the event to actually write the assignment for this, and of course it was very limited. How did you get in, by the way? I couldn't even get in.
Oh, I didn't go.
Oh, you didn't go? Okay. Okay, never mind. All right, so then there's two more events coming up, two more movie events coming up. One is this movie called Sleep Dealer that's being shown on Wednesday. As far as I know, these tickets are they're also on wait list now. But I know that for the Woman in the Moon, some people were getting in at the last minute because people just don't show up. They reserve a ticket, they don't show up. It doesn't cost anything, it's free events. But if you want to catch that, there's an extra credit assignment on TED for that as well. The one you have no problem going if you'd like to, and I really encourage, is if we have our screening of the movie Contact. This is a movie based on a book by Carl Sagan. It starred Jodie Foster. It's back in the 1990s. It's basically what this entire course is about, is sort of Contact for Life. So we're going to be screening that on this Friday from 6 to 8 p.m. Pacific Canyon 109. So all three of these things, if you catch any of these are possible extra credit assignments. Yes, ma'am?
I already watched Sleep Dealer for other class. Is that okay? Am I supposed to go for
What class did you watch Sleep Dealer for?
For dimensional culture.
Nice. Okay, I'll give you credit for it. Yeah, we got to write the assignment.
Yeah.
Okay.
Where do we get tickets for these things?
So Sleep Dealer, right now you can't, the tickets, because you don't pay for them. They're just sort of reserved seats. They're all sold out. So the only way I would say is to show up at Atkinson Hall at 6 o'clock and plead your case as a student that, is in dire need of education. And
Contact not have reserved seating.
so there's a link, but if you go to that page, it just says, wait list only. So you can't actually get any seats.
For Contact as well.
Oh, for Contact, we're just doing this in a lecture hall. So there's no tickets for that. You just show up to the lecture hall. Now, I should say, to prove that you were there, you should take a selfie. And I think that's in the instructions for the assignment. Take a selfie of yourself in the lecture hall. All right. But that's just in the lecture. This is just like the movie we had, the Close Encounters of the Third Kind. It was just in a room. Right, same thing. There's no tickets for this one. But all of these events are because of the other class I'm teaching, the Cat 3 class, which is about life in the universe as well. So usually we don't have these kind of extra events, but we're happy to have them because of the other much bigger class on this topic. Yeah.
The questions are already on for those
Yes.
assignments. Okay.
Yeah, all three of the assignments are now on TED. Okay, any other questions? All right, and the last thing I'll point to is that that class that has all these events, they're starting to show their projects. So if you want to sort of get some last minute ideas of things that you could do, which is very last minute at this point, they're going to be starting to show some of their projects starting today and Thursday, 2 o'clock over in the Sixth College sort of covered area by the parking lot over there. So if you're just curious, there's no extra credit for that. Just want to show up, you can. Okay, questions? Okie dokie. All right, let's do a quick review since it seems like it's been forever since we had class, which was only last Thursday. All right, transit and radial velocity techniques. We talked about the different techniques to identify extrasolar planets. When we combine transit and radial velocity, this allows us to determine what aspects of exoplanets, what characteristics of exoplanets. We should at least 6.
Their size.
Their size, yeah, that's from the transit.
This is from the star.
Is it density?
So orbital properties, so distance from the star. Density, because you get size, and what else? Mass, yeah, that's 4. The other one's maybe a little more tricky. You know the density, what else do you know about the planet, roughly? Internal composition, good.
Radius.
Where's the radius?
Oh, okay.
Whether, like, based on whether it's in the habitable zone or not. Whether it, like,
So that really comes from the orbital properties, so I'll count that as 3b. So remember when we have transits, and so when you have transits in general, it means the planet is passing in front of the star. What else can it do on the other side of its orbit? Passes in front of the star at one part of its orbit, it does what on the other side of its orbit? Passes behind the star on the other side of orbit. Geometry. What happens, what can you measure with that? Do we see anything when that happens? What about the light?
Does it bend?
So interesting idea, because we do see some cases where there is some gravitational lensing, but that's mostly in the case where we have distant stars and planets passing through them that way. Although we have seen this in some planets orbiting white dwarfs, for example. But that's not what I'm looking for, actually.
it's emitting spectrum.
Which emitting spectrum?
Infrared.
No, which
Planets.
the planet, yeah. So when it passes behind the star blocks the planet, which means it blocks the planet's light. And it's infrared light, it's thermal emission, right? Planets have a temperature, they have some kind of emission. They go behind the star blocks that emission. So you see what's called the secondary transit. You see thermal emission. Okay, that's 6. There's actually many more of these things. So we got mass and size, internal composition, the thermal emission. You can also note the composition of the atmosphere, the light that passes through the atmosphere when the planet goes in front of the star. That is absorbed at certain wavelengths by the materials that are in the atmosphere. So we say something about the atmosphere. And one thing we didn't talk about too much was you can actually map the alignment of the planet's orbit and the rotation of the star. It's something called the Rossler-McLaughlin effect. And it's important to note this because what's one of the patterns that we see in our solar system? What's the, between the alignment of the sun's rotation and the planet's orbit? What do we see about those? Are they aligned or are they anti-aligned? Are they random? What's that?
Aligned.
Perfectly aligned?
I thought it was a little bit off. I thought it was a little bit off.
So is the sun alignment and the planet orbit alignment are a little misaligned?
I thought so.
Are you thinking so because I asked the question? Yes.
Is it a few degrees off?
It's actually exactly spot on. It's exactly spot on. So there's our planet, for example, its rotation axis is a little bit off, right? And Venus is flipped upside down, and Uranus is on its side. So the planet's rotation axes are a little bit off. But the sun and the planets in the solar system are all going around in the same direction in almost exactly the same axis, right? That's one of those really key patterns of the solar system that allows us to infer that the planets formed on a disk that was rotating with the sun, right? It's made out of the same material. It started rotating the same way. Everything's rotating together, right? So that alignment is almost perfect in the solar system. But in fact, in other star systems, it turns out that's not the case. And in particular, systems where you have these really hot Jupiters. They're not always aligned exactly the same way. So that suggests that there's something more dynamic going on there. Okay, first planets found were found around what kind of stars? The very first planets. So sun-like stars. Okay.
Yeah, because the first planets that we found were the ones in our solar system.
Oh, that's. All right, I'll give you that one. All right, the next planets after that, first planet's outside our solar system. Good catch.
Pulsar.
What's a star? What's a pulsar?
What was it? After the star.
Dies.
After it dies,
Okay.
there's a concentration of energy, I think. Maybe the second word.
Well, there's a concentration of mass. Do you have an idea?
It's rapidly rotating.
Mhm.
I guess it's a form of star. It sends out, like when it rotates, it sends out beams of some type of radiation. I'm not sure which type of.
We usually detect radio radiation. Actually emits lots of different kinds of radiation. But what's important about those radio, like beams?
It rotates at the same speed, so you can tell like it's the period is constant.
Mm-hmm.
So,
And so why would that be important for finding planets?
um,
Because that is the answer. It's pulsars. Make sure it's clear. Well, so it's a remnant of a dead star. All right, very massive, very concentrated. It spins extremely fast. In some cases, thousands of times per second. This is something the size of, again, sort of Manhattan, spinning around thousands of times per second. That's an incredible amount of rotation. And we see these beams coming with perfect regularity, except in some cases where there's planets orbiting those pulsars. And because the planet gets pulled back and forth just a little bit, those pulses come at slightly irregular times. And we can actually measure that irregularity really accurately. And we can, for the indirect, first planets were found around these very odd types of dead stars, which, we know of maybe a couple thousand of those in the galaxy. But they're found because of this indirect method of finding their pulses at different times. Now, are these good planets for life? Terrible planets for life. Even though they're actually small and Earth-like size, they're probably not in the environments where we want to find them. All right, so first type of planets outside our solar system, found by the radial velocity method, were what kind of planets? Specific kind of gas giants. Well, yeah, okay, so same, but specific type of Jovian gas giant planets. What was unique about them? Yeah, they're hot Jupiters, all right? These very close-in gas giants, which we don't have in our solar system, right? And in fact violates our sort of picture of how our solar system formed. So why did this radial velocity technique find these hot Jupiters first? And find lots of them, actually.
Because it favors large planets that are close to their stars.
Yeah, I think this technique, the radial velocity technique, favors finding, again, this is an indirect method of finding the planet. It finds it by the sort of yank it gives on the star. If you've got a big planet very close to the star, that's going to give the biggest pull, the biggest yank on the star. And so this is biased toward finding these planets, which up until 1995 we didn't think would exist. Right? So this is this example of selection bias. Transit technique, by the way, also has a selection bias finding close planets to stars, because they have to actually align with the star along our line of sight. Right? So both of those are selection biases. The transit method can also find smaller planets. Oops, oh, gave it away. Okay, hot Jupiters are like the outcome of what two possible processes? Those who didn't have like subliminal vision. How did those hot Jupiters get there? We don't have them in our solar system. How did they get there?
Migration.
Good. Migration. What does that mean, migration?
It starts on the outer parts and then it moves it towards the inner part of the solar system.
Exactly. So do you remember how that might occur? Like what's actually causing that migration?
Gravitational pull, and then it goes around.
Well, the sun's pulling all the planets all around all the time. So why did these guys fall in and other ones did not? Yeah.
Another star kind of approached it, and then kind of tugged on the band a little bit. So it's like.
Well, I think you're starting to get to the second reason that hot Jupiters might
Was it
come in.
because it's flowing out?
So that's, again, that's kind of the second possibility, which is scattering, right? Scattering is possible. So if you have another star or another planet even in the solar system that gravitationally interacts with the planet, that might scatter it in or out, and that might be how you get hot Jupiters. But how does this migration occur? It actually doesn't need to have another star or planet to do that. What has to be there? You may remember from the simulations.
I remember there were like this big swirl and I think it was in the middle of the stars, I guess. The star, the one single star, and then it starts like really slow, but they come really fast.
So the swirl isn't in the star, but it's in the stuff around the star. It's the circumstellar disk, right? So the stuff that our planets are presumably made out of, that's the theory we have, and we see these circumstellar disks of gas and dust around other young stars. The interaction of that disk with the planet allows the star to fall in. It's like a big drag, right? It's like it's like trying to throw stuff through water. It slows down. So if you have a planet that's trying to go around the sun and there's all this material in the way, and that's a very sort of rough analogy, that can take away energy and cause the planet to fall in towards the star, at least slowly migrating towards the star. So this is something that must happen very early on in the evolution of a solar system, because that disk of material goes away after about 10 million years. So this is something that happens very early, right? Well before you can start to have life and even possibly terrestrial planets. In fact, this may be wipe out terrestrial planets around some of these systems. Okay, all right. True or false? Most stars probably have planets. Who says true? Who says false? Pessimist. So up until probably a few years ago, we would not have enough information to really answer this. But we now know that most stars do indeed have planets. Now, they're not all of the hot Jupiter kind or even the Earth kind. We'll see there's a mixture of them. But when you add up all the different kinds of planets, the fraction of stars that have planets is actually above 50%. And so that indicates that most stars do indeed planets. And again, that's accounting for the fact that we're missing lots of planets from the RV method and the transit method and all the methods that we find of planets are missing lots of them just because of the selection effects. Even with that, it appears that most stars do have planets, and that's a new fact. All right, are most planet systems like the solar system?
False.
False.
So it's I don't know what this means. So who says true? Who says false? All right, if I think the falses have it, and that's indeed the case. As far as we know today, and again, this picture may change because we're still trying to find other, all the solar systems out there. Most of the planetary systems we're finding are very unlike our solar system. Right? These hot Jupiters are actually pretty rare, so that's not the thing that's mostly different. But even the planets that don't necessarily have these really close-in hot planets have very different planetary configurations than we do in our solar system. And that's something that's interesting when we start talking about the possibility of life out in the universe. If there's not a lot of places that have Earth-like planets, then we may have problems. All right, last question. Earth mass planets in habitable zones have been found. True or false?
True.
Who says true? Who says false? You guys are on and on. All right, up until last year, the answer to this question was false. So this is all of these very sort of new discoveries. This has only recently happened just in the last year or so. And again, I mentioned that, in fact, the person who discovered this first example is a former UCSD student. So go UCSD. But this is, again, kind of how new this field is. We're starting to find for the first time the exact equivalence of our planet out in the solar system. Now, is it exactly like Earth? We don't know, because we don't know what the surface conditions are. We don't know what the atmospheric conditions are. There's all these things about the planet we don't know. Venus is a very Earth-like planet near the habitable zone, and it's definitely not a place that we're going to look for life. So there's lots of things to consider here. Yes?
Is there a difference between Earth mass and Earth-like?
Yes. Venus is an Earth mass planet that is distinctly not Earth-like. So Earth-like, it's a very vague, I'll admit it's a very qualitative, vague term. But I would think of Earth-like as some place that has water on the surface, that has a relatively thin atmosphere so that, you're not under tons and tons of pressure, but some atmosphere so you actually do have an atmosphere. So, somewhere that's kind of like the Goldilocks kind of place where life can form. I would say that's Earth-like. Yeah, it's kind of a qualitative term. That's why I use Earth mass. Okay, any questions on these? Yes, sir.
Going back to the pulsar thing.
Yeah.
In a previous class, did you say they've only found 4 planets in pulsar?
So there are 4 that are definitely confirmed. There's
Okay.
like maybe 7 or 8 if you include sort of some candidate planets. I mean, if you remember, the planets that are around, at least the ones that are confirmed, are very low mass. There's, one's like a Mars mass, one's Mercury mass, and one's like a tiny little rock. And that's only detectable because we can measure those pulses so accurately. You see very tiny perturbations. So there's a few more that are probably small planets, but because they've only just been found, they need to be verified.
Because I remember reading about it, and they said they found 3.
So there's 3 around one star. In fact, there's maybe a 4th one.
Yeah.
That's
So
a candidate.
the 4 confirmed ones are when they first discovered.
No, the 4th one is still a candidate.
Or okay.
So there's 3 around that first one, D1257, and then there's a second one that has a planet, and there's like 2 or 3 more pulsars that seem to have pulse variations that may
So the technique isn't very popular with them, right?
It's not very efficient now.
They
So
did it in 1992, I think.
yeah. So they found like 4 in
Yeah.
20 years, whereas the transit method has found now thousands, and from Kepler alone, that's just in the last few years. So it's good to have multiple techniques because you find different kinds of planets through different techniques, and every technique has its own biases. So it's important to look at different parameters. You're exploring parameter space with your homework assignment, but some techniques are just not very fruitful, but they still find interesting places. Okay, any other questions? Okay, so today we're going to we've talked all sorts about the different kinds of worlds that are out there, and now we're going to get kind of the nitty gritty this week is, now that we have all this information about what our solar system is like, what life is on the Earth, what kind of planets are in our solar system, what kind of planets there are out in the universe, is there a possibility of finding life out there? What is the likelihood that we will someday actually see that there's life off this planet? And this is based on all the sort of facts that we've been talking about. So again, this sort of very recent result just last year of finding habitable worlds. We know that habitable worlds exist outside of our solar system. So we know that there's at least a possibility of finding life beyond Earth and beyond our solar system. We know that at least in one case, life is very abundant on a planet, and that's here on Earth. It's been abundant on this planet for about 3 billion years, 3.5 billion years. It started very early on in Earth's history, so it seems like if you got the right conditions, maybe life can take hold pretty quickly. And then, the other thing is we think about not just basic forms of life, but forms of life that we might actually talk to. All right, we know that intelligent life exists on this one place of a sort. All right, depends on your definition of intelligence. But we know that there's a technologically advanced civilization on at least one planet. So the question is, are there other technologically advanced civilizations out there, and how would we actually quantify how many of those might be, and how would we actually find them? So it's again important to go back to this idea of habitability, right? What kind of worlds really are places where we'd expect to find life in the first place? And so, we mostly talk about habitable zone as a place where you have liquid water on the surface, and this defines the habitable zone around the star. It's important to note that that habitable zone, of course, depends on what type of star you have, and you explore this in homework 6. And if you have a massive star, that habitable zone moves out. If you have a low mass star, the habitable zone moves in. That's all dependent on the temperature of the star itself. And so if we were to plot that different types of stars, so the sun's up there, and you get the cooler and cooler stars down here, and then the distance from the sun or the star in which that water can exist on the surface. You see this kind of band. This is on a log scale, by the way. So up here at 1 AU, you can see the Earth, and then you can see that Mars is also somewhere situated around that same place. And then you see all these other crosses of different planets around, different mass stars. And you can see that, in fact, there are quite a few little planets that happen to be in this strip of habitability. That strip, again, being exclusively defined by the presence of water on the surface, right? The conditions in which water could exist if you have an atmosphere. Now, of course, this is not the only possibility. We've talked about, that the moons out in the outer solar system, where it's way too cold to have liquid water, could have water under the surface. So this is a very restricted definition of habitability. Nevertheless, it's important to note that this is something that depends on the type of star. Where those planets have to be depend on the type of star for them to have water. Now the problem is you can get a little bit too close. This is kind of the same plot in slightly different scale. This is now mass in units of solar masses. So this is in the sun right here. Here's a tenth of the sun mass. And again, this is distance from the sun in astronomical units. And this is that same habitable zone that I showed in the last plot. Okay, here's the Earth sitting nice and happy in it. This line shows the point at which tidal forces between the star and the planet start to force the planet into alignment, facing the same face toward the star. Now we see this today with the moon, right? It's not a coincidence that the moon is rotating at exactly the same rate at which it is orbiting around the Earth, which allows us to just see one face of the moon, right? It's just going like this the whole time, rotating and revolving at exactly the same rate. That's not a coincidence. That's tidal forces that have slowed the moon's rotation down and forced it into alignment with the Earth. By the way, why aren't we showing the same face to the moon all the time? Why is the moon tidally locked to us, but we're not tidally locked to the moon?
Moon doesn't have as much of a gravitational influence on the Earth as we have on the moon.
All right, so this is a good physics 1 question. Does the moon exert a smaller or greater or equal gravitational force on the Earth? Who says smaller? Who says the moon exerts a greater force on the Earth? Who says it's equal? Good, you all passed my physics 1A class. Equal, forces are equal and opposite. Any two things that are experiencing a force between each other experience the same force, equal and opposite. That's Newton's third law. But what's different between the moon and the Earth? One of them's a lot more massive. So even though it has the same force, the acceleration, or the, at least in this case, torquing, that the angular acceleration that the moon and the Earth experience are very different, because the Earth is so much more massive. Even though that force is the same, it doesn't turn the Earth as hard as it does turn the moon. So, it's the asymmetry of the moon and Earth mass that has forced the moon to be in this tidal lock position. And similarly, if we're looking at terrestrial planets, those are much smaller than the stars. And so if they get too close to the star, they will also be tidally locked up so that they face the same side toward the star. By the way, same thing happens with the moons around Jupiter. Those moons all face the same side towards Jupiter because of this tidal locking. So it's a very common process in planetary dynamics. Of course, the problem is if you have a planet that is just facing one side towards the sun, then that planet is getting super hot on one side and not hot on the other. So you have these very extreme temperatures, and it really restricts the area in which life could actually develop, right? Even though this may sit in the habitable zone, it is going to be way too hot on one side because it's getting sunlight all the time. It's going to be way too cold on the other side. It's actually not going to have surface water, except maybe on a sort of twilight zone in the middle of it, right? Now, by the way, there's a caveat to this, and so there's two things. So you get extreme heat and cold, but also the rate at which you're rotating becomes exactly the same as the rate in which you orbit around the star, and that could be a very long time, right? We have a strong magnetic field because we spin around once every day, but if we spun around once a year, we probably wouldn't have enough rotational energy to generate the kind of magnetic fields that we see here on Earth that protect us from the solar wind, right? Again, Venus is a great example. Very slow rotation rate, zero magnetic field. Right? You need to have rotation to have a strong magnetic field. And that's one of the things that's important for habitability here on the Earth. So two things really kill you if you're inside this tidal zone. Now, one caveat, this planet right here, anybody know what planet this is in the solar system? Yes, the closest one to the sun is Mercury. Good. So anybody know about how Mercury rotates compared to how it orbits? Is Mercury tidally locked?
Then it turn around in the opposite direction.
That's Venus. Venus turns around in the opposite direction. What do you know about Mercury?
has a longer, it's longer than its orbit.
It's actually a little bit shorter than its orbit. It's actually in what's called a rotation orbit resonance. Right? It rotates, I think, something like 3 times or every 2 times it revolves around the sun. These kind of resonances are not too unusual. They happen in some multi-planet systems that we're finding, and also happen in multi-moon systems. This wasn't, by the way, this wasn't known until the 1960s. For 1960, most people thought Mercury just faced one side of the sun, just like the moon faces one side of the Earth. It was actually a big surprise to find that Mercury actually has a slightly tweaked rotation. And the other interesting thing is that Mercury also has one of the largest eccentricities in its orbit among all the planets. And this is probably why it has this sort of asynchronous rotation. So even though it is within this line that says you should be tidally locked, always facing one side toward the sun, you can have some additional dynamic effects that can force you out of that line. Now, regardless, Mercury is not a great place to live. Right? It's much too hot. There's not a lot of water. So much, everything would evaporate. It has evaporated a long time ago. But it does suggest that it may be possible to have slowly rotating planets, but they're still going to have problems with no magnetic fields, and that may still kill the possibility of habitability on those planets. Yes, ma'am.
I have a question about the habitable zone. Like Earth is kind of like on the verge of it. I mean, it's in like within the habitable zone.
Yeah.
But, is it possible that habitable zone can be like a move? It can be moved away from it, right?
Yeah. So we talk about this. What's going to happen to the sun as it gets older?
It's gonna get big.
It's gonna move
And
the,
hotter.
Well, so at some point it's going to get really big. But what is it going to do sort of in the, what is it doing really slowly right now?
it's getting more luminous.
It's getting more luminous, it's getting hotter, and that's because it's been running out of, it's using up its hydrogen in its core. So in order to keep those fusion reactions going, it actually burns faster, produces more energy, and it's getting brighter and more luminous over time. This has been happening since the sun formed. So this habitable zone, because the sun's getting hotter, has been moving outward. And that's why we think Venus early on may have been the right conditions to have water, because it was a cooler star, and so the habitable zone would have been closer to the sun, and Venus would have been right smack in it. So this is going to move out, and we are in sort of a bad place because we're on the inner edge of it, and so we're on the edge that started to move out, or it's been moving out the whole time. So time is an important thing too. How long you actually spend in the habitable zone depends on how wide the habitable zone is, and how long it takes your star to evolve. So we're probably going to be out of the habitable zone in about 1 billion years. So have fun now. All right, so that's all to do with just that, location where water can exist on the planet. Lifetime is an important fact. One of the things we haven't had a chance to talk about stars in great detail, but stars have different life cycles depending on their masses. More massive stars burn up their hydrogen much more quickly, and so they have shorter lifetimes on the main sequence. And so if you actually plot the time that stars are burning hydrogen, that's what we call the stellar lifetime. When we say stars die, it means they've burned through all their hydrogen, and they're either going through sort of various phases of sort of burning other stuff and exploding and stuff like that. But we can identify a sort of time scale as a function of mass. And again, here's the sun, which has a lifetime of about 10 billion years, right? And here are the different time scales from when sort of important time scales for life on Earth, right? About 10 million years after the sun formed is when the Earth formed, so you need at least that much time to actually make planets in the first place. Microscopic life, we think, started maybe somewhere around several 100 millions of years, maybe 500 or 600 million years. Actually pretty quick. Considering we've been around for 4.5 billion years, but still a long time period. And then, of course, complex life. This is that the Cambrian explosion, when life starts to colonize land, and you see trilobites, and you start to see complicated animals. That really doesn't happen until something like 4 billion years into the sun's history, right, in the last 500 million years. But if you have a star that doesn't live longer than, say, 100 million years, you don't get to these points, right? Now, it may not be that this is the time scale that's universal, right? Again, we have one example. That's the only thing we have to go on. So maybe some of these stars, life can form much more quickly, and they can evolve much more quickly into forms of complex life much more quickly. We don't know. We have one example of this. But if any life is like life on Earth, you're going to have at least, something like 4 billion years in order to get to the point where you have complex life that's actually residing on it. All right, so that sets actually a range of masses, or at least maximum masses, around which, stars around which we would expect to find life. And that maximum mass, if you want just life, is going to be less than 3 times the mass of the sun. If you want complex life, it's got to be less massive than about 40% more than the mass of the sun. Which is, if you think about it, wow, we just snuck in, right? We're 1 solar mass, and sort of the limit for complex life, at least if it's like Earth, is only 1.4 solar masses. So we would expect to find a lot more life around lower mass stars because they live longer. Another possibility is, one reason that these massive stars are bad as well is that they're very hot and they have higher energy radiation, right? Their black body spectrum is more towards shorter wavelength light. So there's more UV and X-ray radiation. And at least, again, life here on Earth does not do very well in the exposure to high energy radiation. The energy from ultraviolet and X-ray light is the same amount of energy as the bonds that bond carbon together and carbon hydrogen together. Same kind of energy. So when you bathe an organic molecule in ultraviolet light, you break that molecule up, right? The light forms actually breaks up the chemical bonds, which is great for, sanitizing things, right? That's why we use UV radiation to sanitize, meats and stuff like that. But sanitizing is not good generally for the development of life. So if you have an environment where you have very high energy radiation, you're unlikely to have the same kind of chemistry that we have here on Earth, which is based on carbon and hydrogen and oxygen. So that's a problem. Stars are also found in multiples, and it's often difficult to have stable planetary systems when you have multiple stars. We have seen examples, again, very recently, of planets that are orbiting multiple stars. In some cases, they orbit around both stars, just like a Tatooine-type planet, right? More often, we see a planet orbiting one star, and there's 2 stars in the system orbiting around each other, right? So that's also a stable system. But if you have a case like this, where you've got 2 stars and a planet that forms somewhere in the middle, this sort of 3-object dance is very unstable and very quickly falls apart. And usually it's a planet getting kicked out somewhere else, right? But this may be the source of these sort of wandering planets that we think may exist and are starting to find some evidence of, right? Maybe that they form in these sort of unstable hierarchical or unstable triple systems or quadruple systems, right? But if that's the case, they're not going to be stuck in the habitable zone for very long, because they're going to go shooting out into deep space, and that's kind of it for habitability. Right? So whether you're orbiting a single or multiple star is something that's really important as well. And importantly, most stars in the galaxy are in multiple systems, so this starts to restrict the number of places where you expect to have planets. The last point is that the other elements of life that we need are these special elements: carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. Right, 98% of the elements that make up life, and we've seen why those elements are so important in life. But it turns out that the distribution of those elements is not uniform throughout the galaxy. There's something that's known as the Galactic habitable zone. It's sort of a ring around the galaxy, where the abundances of elements seem to be just about the same as the abundances of elements in our sun. So if that's the optimal element composition, then we may only find habitable worlds in this section of our galaxy, which actually turns out to be a relatively small part of our galaxy. Our galaxy actually extends way beyond what you see in this visible light image. Of course, this is not a picture of a galaxy, because I can't take a picture of a galaxy from the outside. This is just a model of it. But it really restricts where in our galaxy we might expect to find habitable worlds, just based on the elemental composition. Right? Way out here in the outer skirts, there's very few heavy elements like carbon, oxygen, and nitrogen. And way here in the middle, there are plenty of elements, but it's also a very high radiation environment because there's so many stars. So there may be just places in the galaxy where we'd expect to find habitable life and places we don't. That's another consideration. All right, so taking all this together, we can ask how many habitable worlds are out there. We know there's something like 200 billion stars in our galaxy. And if we break down the number of stars by mass, what we find is that there's about 25% of them have masses in this range. Now remember, this lower limit is set by that tidal locking, right? The lower the mass of the star, the closer the planet has to be. If it gets too close, it's tidally locked. Not a great place. So this sets the lower limit. And this upper limit is the lifetime of the star, right? The star dies too quickly. You don't have time for life to evolve. So that sort of that gets rid of 3/4 of the stars in our galaxy that could be possibly a host for life. Only about 10% of these are in this galactic habitable zone, right? That's a small fraction. We now know that at least half, maybe a bit more than half, of these type of stars have Earth-like planets, either Earths or super Earth-like planets, and so that maybe half don't, so that gets rid of some fraction of those, and then only maybe about 10% of those planet systems are going to have planets in the habitable zone. This is a bit of a guess because we haven't quite figured out exactly the fraction of planets in habitable zones. But if you look at our solar system, we've got 1 planet out of 9 in the habitable zone, or 1 planet out of 8, right? Depends on what you count, right? So that's 1 in 10 roughly, right? Give or take. So if you add, multiply all these numbers together, you get down to something like 250 million habitable planets in the galaxy. That's still a huge number, right? This is still not rare. It seems to be a lot of possible worlds. And of course, depending on how you make these estimates, you can have a range, right? It could be 10 million, it could be all the way up to 10 billion, right? This sort of shows how unknown these numbers are, this sort of huge range. But it does suggest that there's lots of places where habitable zones habitable worlds might exist. So we should start looking for them, right? How do we go looking for them? Well, it depends a little bit on how we actually want to find, what kind of life we want to find. If we're just looking for simple life forms, right, little bacteria and microbes, the things that have been around on our planet for billions of years before we started walking around on it, we have to start looking for the products that those life forms actually produce. And one of the best ways of doing this is looking at what the atmospheric compositions are. So this is just showing what the sort of roughly the how much material we would see sort of coming up off the surface of the planet for different elements. Okay, so you have stuff like hydrogen, methane, right? You have some of these things like dimethyl sulfide are only found as life forms, and you can compare how much of this stuff would you expect to find on the planet on something like Earth, and how much would you expect to find on the planet that doesn't have any life forms. And it's a very different molecular composition, right? Our atmosphere is almost entirely sort of generated or at least modified by the life forms that have been on this planet, right? Just thinking about the oxygen in our atmosphere, no other planets in our solar system have oxygen in the atmosphere. All that oxygen is produced by photosynthesis. So life has had a significant impact on what our atmosphere looks like. And so if we can study the atmospheres, and we know we can do that with transit spectroscopy, then we can actually look for the chemical signatures of life in those atmospheres. So that's one way we can look out for life. Here's just another example of this. This is showing the spectra in the infrared. So this is wavelength in microns around a few strong molecules. And you can see here's Venus, and here's Mars, and here's the Earth. And all 3 of these planets have carbon dioxide in their atmospheres. Even though the Earth has a very small fraction, you can still see it in the spectrum because it's a very strongly absorbing molecule. We can see, for example, in Venus, hydrogen sulfide. You don't see that on Earth or Mars. What Earth has that Mars and Venus don't have are both water and oxygen, in particular O3, this ozone. Right? Why is ozone so important, by the way, for life on Earth? Other than being a product of oxygen, why is ozone? It does. It exactly blocks UV. So the absorption you're seeing here, this is in the infrared, but if I went over to the UV, which would be over here, you would see another very strong O3 feature. And it's important that that's there because that absorption is actually absorbing the UV radiation that would damage our cells. So detection of O3, not only does it tell us that, hey, there's a source of oxygen, which really shouldn't be in these planetary atmospheres, but it also indicates that the surface of this planet is probably protected from ultraviolet light, which means that the chemistry that we see in life is also protected. So O3 is one of these signatures that people are looking very hard in the spectrum of planets, because if you see it, that's a really strong indication not only of life, but the conditions that can really allow life to develop and evolve. And again, we're starting to be able to do that now with the technology we have. Even if you don't look at spectroscopy, you can also just look at the colors of planets. All right, a very, very simple snapshot picture of a planet might tell us something about whether life is on it. This is kind of just an infographic, but it shows the sort of ratio of red to green light here on the bottom axis and blue to green light on the vertical axis. And all the planets, you can see that the gas giants are all over here on this side, and the terrestrial planets on this side, but Earth is standing out here all by itself, right? Just based on its color. Now this tells us that it's a very blue and very red looking planet. The blueness, of course, is from the ocean water, right? Where does the red color come from? Anybody know? Or actually, let me take a step back. So go ahead. Say again?
Iron.
So we do have some places that have iron on the surface, right around volcanoes and stuff like that, but those aren't huge sections of the planet. Yeah.
The landmass, my continents.
Yeah, so the continents, so there's some, so part of the iron is in the volcanoes around the continents, but we also have just desert, which is kind of brown, which looks a little red-ish, depending on, what's in the sand. So it turns out that, in fact, a lot of this red light, which is kind of surprising when you think about it, is actually coming from the plants themselves. Right? There's something called the red edge that is the result of photosynthesis absorbing light on the plant. Right? Photosynthetic compounds in plants are very efficient at absorbing red light. Right? And the fact that plants are very strikingly green a lot is because the red light has actually been absorbed out of them. So has blue light, as it turns out. Right? The green light is reflected. And so the sort of absorption by red light allows Earth to actually have a sort of slight tinge to it that these other planets don't have. And there's folks that also look for this sort of red edge and, again, pictures of planets to see if they can see for evidence of photosynthesis. Now, there's no reason to think that other life forms would develop photosynthesis. That might be something that is just unique to the Earth. But, these are just basic chemicals. And so maybe it's not too crazy to think that that's a pathway that's very common to develop. So there's multiple sort of ways that we can maybe approach looking for simple life forms based on their effect on both the atmosphere and also just their sort of coverage of the planet that we can take pictures of. And we're just starting to get to the point where we can start doing this. Now, that's one form of life form. All right. Another form of life form, of course, would be someone we could talk to, and those are the aliens. Right. So where are all these aliens? This is something that Enrico Fermi, who was a famous physicist back in the early part of the 20th century, he's a famous physicist because he's basically the father of sort of all of nuclear physics. He developed the first nuclear reactor. He was key to sort of developing the first nuclear weapons, and then he was an outspoken critic of nuclear weapons afterwards. But he also thought about sort of big problems from an estimation point of view, sort of thinking about numbers and saying, how can I estimate something like this? And he did the calculation we just did before, but how many potentially habitable worlds might there be in the galaxy, and came up with a similarly extremely large number. And thought about this and said, well, look, not just the galaxy, but the universe is so big, right? And there seem to be so many habitable worlds, and we know that at least on this habitable world, we have intelligent life forms. And we've only kind of recently gotten into technology, right? So you can imagine if we're around for another couple 100,000 years, we'd have fairly advanced technology, right? Almost like magic. So there's all these sort of habitable worlds and potential for advanced life forms. There should be advanced life forms all over the place, and they should be super advanced. They should be colonizing the entire galaxy. So where are they? Why don't we see them? So this question and so it's a more scientific way. This hypothesis seems inconsistent with lack of observational evidence to support it. It says, where the heck are the aliens? Right? Why don't we see the aliens if this is, it seems likely that you can have life throughout the universe? So this question has been known as Fermi's paradox, and sort of the search for intelligent life is really evolves around this question, right? How do we quantify, how often does intelligent life arise, and how do we actually look for them, and why don't we see them? Are we missing them, or are they just not there? Right? These are sort of the outstanding questions in this field. So asking the question of how many civilizations might be out there is something that this person, Frank Drake, sort of started asking back in the 1960s. You're going to hear more about Frank on Thursday. Professor Shelley Wright's going to be talking about the SETI project, which I may get to just briefly at the end here. But that's the search for extraterrestrial intelligence. This is the effort to actually look for aliens that have intelligent civilizations that are communicating through space and stuff like that. And Frank Drake was one of the early proponents for this idea. And he also thought about this quantitatively. How would you actually go about estimating not just the number of habitable worlds, but the number of intelligent species that might be out in the universe? And he came up with this equation that's written over here. So this is the equation. It looks like a really crazy, silly equation with lots of strange letters. But this is really just kind of a way of organizing our ignorance about this question, right? To ask how many intelligent civilizations out there actually asks a lot of sub-questions that we have to sort of figure out and piece all together. So this is what all these different questions are. So we'll go by this one by one. So this first number here is just asking essentially how many stars, can we look for alien life around. We know that today that's 200 billion stars, but we can also ask this in the sense of how many stars are formed every year, right? Because every year you form some stars, every year there's some civilizations that exist, and that'll give you some idea of the number of civilizations. So this is a number that's known, the average rate of star formation in our galaxy. It's something like 20 stars per year. Right? So that gives us a starting plate for at least places to look for planets. The next question is next factor here, FP, is one that we've just started to get real limits for, and that's the fraction of stars that have planets. And as I said, that fraction seems to be at least the majority. This is a plot I've shown before showing the breakdown of different types of planets and the fraction of stars that have at least one of these types. And as I mentioned, if you add up all of these different varieties, you get over 50%. So more than 50% of stars have planets. Of course, maybe only a third have the kind of Earth-like planets that we're particularly interested in. But of course, then you also have to count the moons around these Jupiters and ice giants and stuff like that. Who knows how many other worlds there are, right? So at least there seems to be 50% of stars have planets, and probably more because many of these stars have multiple planet systems, so multiple chances of finding life around them. That's the limit of our real knowledge. After that, we start to get into some unknown numbers. All right, so we may know the number of stars number of planets around each of the stars. We don't know how many of those planets can support life. Right? We talked a little about this in our scale of the solar system. Here are the sort of inner terrestrial worlds except Mercury, and here are sort of the 4 of the big moons out in the outer solar system. And we really can only rule out life on one of these, which is Venus. Right? Venus is much too dry and much too hot to have life forms. But we still can't rule out subsurface life on Mars or on Ganymede or Europa over here or Titan or Callisto. All of these may have subsurface life because they may have ocean waters underneath the surface that are being heated by tidal friction, at least down here in the bottom parts. All right, so we actually don't know an answer to this even in our own solar system. So this is an unknown number. What fraction of the planets in a given solar system can have life or habitable for life? It could be all of them, it could be a significant fraction, or it could be one, like the Earth. We don't even know that in the solar system yet. So that's an unknown number. What fraction of these habitable planets can actually develop life? Again, we only know one for sure, and we don't know about the rest. Right? These are still questions. No idea. It could be this is 100% formed life forms, or it could be that one, like the Earth, forms life, even though it's habitable. We don't know that answer, even in the solar system. So now we're starting. So this is, so we get to the point where we have life. What fraction of these life-brain planets can you actually get intelligent civilizations? And this is where we really get into speculation because, again, we only have one planet, which we know has life, and we know it has intelligent civilizations. But of course, if it didn't have intelligent civilizations, we wouldn't be asking what fraction of planets have intelligent civilizations because we wouldn't be around. Now, so there's two kind of words here. There's intelligence and there's civilization. Intelligence is something that's very qualitative, right? We have plenty of animals on this planet that are extremely intelligent. They have social behaviors. They have forms of communication. They use tools, right? But so how do we actually quantify this? It's not just brain size because, elephants and whales have humongous brains, but they don't, tap texts at 100 characters a minute on their phones because they don't have phones, all right? So it's not just brain size. People think that, in fact, it's some fraction of sort of the brain to body mass is a way of estimating intelligence. And of course, it's a way of estimating it because we happen to come out on top on that particular number. But there are many species that are very close. So this encephalization quotient, the ratio of body mass to brain size to body mass, we're sort of on top of that, but there are other creatures that are fairly high. And I should say it's not exactly a perfect brain to body mass, because it turns out birds have a much higher brain to body mass ratios than we do because their body masses are so light because they fly. But they're also not writing things, although they have some very, very intelligent behaviors. Now, the important thing is that you can actually estimate this kind of ratio going back into the geological record. We can look at the sort of brain cavities of early humans and of primates. And we have lots of evidence that across the sort of different species on the planet, this encephalization quotient has continuously gotten larger and larger over the course of the history of life on Earth. So that suggests a positive evolutionary pressure to move towards more intelligent species, at least in the one experiment that we have any measurements for, which is here on Earth. Now, civilization is another thing, right? If you take a humanities class, you can write down all the possible sort of characteristics of civilizations. Obviously, social structure is one, but there's all sorts of different sort of characteristics. This is highlighted because this is for my CAT class, so culture, art, technology have to be important aspects of civilization. And again, we don't know if this is a natural consequence of intelligent life forms, right? We certainly see animals that have social structure. We have no idea about religion, although there are certainly many instances of, for example, crows have behavior that suggests mourning of death. They have sort of what look like sort of funeral rituals. You see crows that, I have a great video of a crow that's dying on the ground, and the crows around them are circulating and calling out. It suggests some kind of, complex social behavior. Now, and we have a fantastic stable food supply in our garbage cans. So maybe this is the rise of civilization, but we don't know about any of the other stuff. But the amazing thing about, at least in terms of human beings, civilizations cropped up across the planet, all at roughly the same time, at least within a few thousand years of each other, and in cases where you have essentially no contact between those groups. So the earliest civilizations we see are here in the sort of Middle East and the sort of Tigris-Euphrates valleys. But we also see civilizations popping up out here in China just a few thousand years later. There's probably contact between these groups, but there's certainly no contact between these groups and these groups over here in the Americas. And yet they developed essentially the same patterns of civilization. In some cases, essentially the same patterns of building, right? There's pyramids in Mexico that look a lot like pyramids in Egypt. All of these were happening independently, and it suggests that maybe a civilization, an organization of civilization, is something that's very common, at least when you reach to a certain level of intelligence. Again, completely speculative, because we've got one example, right? Human beings. That's it. So we're left to sort of wonder how often this would actually happen in other worlds. All right, so that's unknown. And then you have to go even further than that. You can have an intelligent civilization. You can have a pod of dolphins that's talking to each other. But are they actually a pod of dolphins that we can communicate with out in space? And so this next fraction talks about the fraction of civilizations that communicate across space. And that's a fairly recent outcome of our particular species because it requires electromagnetic energy. It requires the intelligence and the tools to harness electromagnetic energy. And it requires electronics, which really kind of rules out dolphins from being a communicating intelligent civilization because it's hard to build electronic radios in seawater, right? With flippers. So this starts to sort of pin down our numbers a little bit more. Now, we have been communicating out in space for about 100 years now. Our first radio broadcasts were made in 1906. This is a picture of Marconi with the first sort of radio transmission device, and he sent a message between the United States and Europe back in 1906 or 1901. So we've been broadcasting for about 100 years, and those broadcasts are just going out into space. They're leaking out into space in all directions, which means by now, those broadcasts have reached about 500 sun-like stars. That's how many sun-like stars we have within 100 light years of our world. So, in principle, we have been a communicating civilization for quite some time. Even so, 100 light years is a tiny, tiny fraction of the size of the galaxy. Anybody remember how big the galaxy is across in light years? Yeah, of order 100,000, 50,000 light years. All right, so we would have had to be communicating for 100,000 years to actually reach everybody, and we certainly are not doing that. We're a very new communicating species, and nonetheless, there's still plenty of stars in our neighborhood that, if they have sufficient sensitivity, could actually detect those communications, and vice versa, right? If there are worlds nearby that have started their communicating recently, perhaps when we have enough sensitivity, we could pick up those transmissions as well. And that's what the whole purpose of SETI is. Yeah.
But isn't there a limit on like how much they can pick up as like the radio waves weaken over time?
They weaken as 1/distance squared, right? So this is a whole question of how advanced does a civilization have to be? We are only starting to detect radio signals in space in the last 100 years. The other civilizations have been doing it for 100,000 years. This is probably a no-brainer. Who knows? All very, very speculative. Okay. All right, and then the last and probably the most important factor in the end here is how long such civilizations last. And again, this is a speculative question because we have one example of which we don't actually know the outcome for, fortunately, right? So, as a civilization, we appeared on the planet as a genus about 2 million years ago. We appeared on the planet as a species only about 200,000 years ago. Our first civilizations are within the last few thousand years. We've only been technologically capable to transmit out into space in the last 100 years. And of course, almost immediately after that, we start building weapons of mass destruction. So a good question is, a species that's capable of the technology to travel to the moon, for example, are they also capable of technology to build tools that will also wipe out their civilizations? And we have no idea. Right? We have no idea what that number is, fortunately. Right? We asked this question maybe 20 years ago. People thought it's about like 50 years because we're about to go into nuclear holocaust. I think we've actually passed that time where that's a major problem. But, asteroids hit the planet. There's all sorts of things that we can cook our planet based on carbon dioxide release. There's all sorts of things that can limit the lifetimes of civilizations. And we simply don't know what that number is. So all of these things factored together give you some estimate of, at least in sort of this framework, some estimate of number of civilizations. So you can start plugging in numbers and guesses for these things. And so, for example, if I want to make a guess that, the number of planets that can support life in any system, let's say there's one, like the Earth, all right? And the fraction of habitable that actually develop life, so the Earth is habitable and it developed life, so I'll say that's 100%, right? And maybe only 1% of those kind of planets develop any kind of intelligent civilizations, and only 1% of those actually build the technology to transmit and communicate and travel into space. And those last for 10,000 years, which is a pretty long time, right? We're only 100 years in. 10,000 years is a much longer time. But multiply all those numbers together, I get something like 1. In the entire galaxy, 1 communicating intelligent civilization. And that's assuming we last 10,000 years. So that's kind of disheartening, right? But of course, we don't know what these numbers are, so let's play with them a little bit. Let's say that there's a lot more, the fraction of planets is much higher. It's like 3/4 of stars and planets. And let's say every one of those stars, they have 3, different planets that can form life. And all of those planets, all of those habitable planets actually develop life. That should actually be a 1. And anytime you have life on a planet, it immediately goes to intelligence. And anytime you have intelligence, it immediately goes to transmitting broadcasts. And those things last, those civilizations last for 100,000 years. Then you've got tons and tons of intelligent communities, 13 million. You can see the range of these guesses by how uncertain we are about these completely speculative ideas. Right? We could be the only civilization in the entire galaxy today, or we could be one of millions. We simply don't know because we don't know these numbers. Okay, so in the last 5 minutes, I want you to take a moment and write down your guesses. Make sure you put your name on, ignore the cat tree on the top there. Write down your guesses for these numbers and justify them. And see how many civilizations you get as a result. Oops.
So, like the numbers, can be anything?
The numbers can be anything,
Okay.
but you have to explain why you chose that number.
Okay.
So the first two I'm going to give you because that's actually something we kind of know, right? Everything after this is entirely up to you, but think of a reason why you're choosing that number. And then when you're done, multiply all those numbers together, see what you get. Okay, it needs more time.
I got about 5,000.
Okay, I'll do a poll in this moment. Is anyone still calculating? Okay, how many many do you get somewhere between, how many get less than 1? 1 gets less than 1, okay. How many get between 1 and 10? 10 to 1,000. Okay. 1,000 to 1,000,000. Okay, how'd you get?
What?
Yeah, right at 1,000. Okay, all right, I'm counting 1,000 here. All right, more than 1,000,000. Okay. All right, so just for, and I don't think that adds up to numbers. So
Yeah, me
class,
too.
all right.
Yeah, I'm 10 to
You get 10 to 1,000. So the remarkable thing is that in every class I do this in, it's pretty close to the distribution. Usually I have more numbers, but that's pretty close to the distribution. That there's a lot of sort of optimists, I would say, in terms of number of habitable worlds out there, and occasionally a few pessimists as well. But the interesting thing is that these are big. This is uncertainty by orders of magnitude, right? And again, it's because we really don't have a handle on these numbers. Now, on Thursday, as I mentioned, Professor Wright is going to be coming in here. She works on the SETI project, and she works on the project that actually seeks to quantify some of these things more precisely by looking for intelligent civilizations. And so she'll talk a little bit more about the sort of efforts to do that. Wednesday, so tomorrow we're going to have our discussion section at 4 o'clock. Your lab books are in the back. If you want to pick them up and bring them with you Wednesday, otherwise I will bring them with me Wednesday instead. But we're going to talk a little bit more about sort of the next step after sort of quantifying is how do we actually go and identify and communicate with civilizations. Any questions? Are you surprised by your numbers? All right, go ahead and turn in your written forms up for the front corner here, and I will see y'all on tomorrow. Wednesday.
Where'd you get it?